Thanks very much. Thanks, everyone. Special thanks to Daniel for the very kind invitation to speak here, even though I'm sort of a bit of a tangent to this conference. This talk is about a certain class of semigroups and groupoids, and it's seems to be on. Okay. And it might be a stretch, but I could sort of consider this as categorifying semigroups. Also, I gave a version of this talk at the Sunshine Coast recently, and when I was about to update the title page, I just couldn't bring myself to do that. So anyway, so this is all joint work with my postdoc Azeef, and this is again at the Sunshine Coast doing some maths. The talk is about this paper. It's on the archive recently. It's a fairly big paper, so I'll give you basically the idea of the main result from the first half, mention a couple of applications. And this is not just a general comment. We were looking at the registration page for this conference, and we both got the sanity check question wrong because I'm ashamed that I forgot my representation theory class for Andrew 20 years ago. I forgot that you have to swear the dimensions when you add them to get the order of the group. Yeah, so I told Azeef, oh, that's 6. That should have been 4. So the main theorem in this paper, in the first part of the paper, is that the category of this well-known class of semigroups, which we'll talk about, is isomorphic to a category of something that I've got in quote marks here, because essentially we had to make these up, or we had to figure out what they were. And this talk will tell you what this theorem is about and give you some idea of how it works. So in fact, a large part of the talk is going to be about the background for this stuff, because I don't assume everyone here is a semigroup theorist, and in fact, I know that most of you are not. But the basic philosophy goes back to a quote from Mark Lawson in his book about inverse semigroups, which is an excellent book. It says groups model symmetries, some other words, and then inverse semigroups model partial symmetries. So the very sort of slogan version of this is that if you're studying groups, you're really studying permutations. So one of the undergrad results is that any group embeds in a symmetric group, in particular in the group of permutations of itself. And there's a version of this for semigroups, where you just have semigroups being essentially groups of functions, not necessarily injective or bijective ones. But there's a specialized version for the class of inverse semigroups, which I will define shortly. And they're essentially inverse semigroups of partial bijections. So this is sort of a couple of lines of proof. This is quite a deep theorem, even though it's essentially the same in flavor.
Partial in what sense?
So partial, like think of something like the log function, and we think of that as kind of a function from the real numbers to itself, even though it's not defined half the time.
So it's just partially defined.
So it's basically a bijection between subsets of your fixed universe, something like that. These are slogans, and soon I'll have something more concrete. So if you read Mark Lawson's book, you find a very interesting survey of the history of this topic. This is kind of a one-sentence summary of that, which is that once mathematicians found all these non-Euclidean geometries, they were studying them, and in some cases you try and work out the automorphism group, and there was just nothing, even though the spaces looked obviously symmetric in some way. And people were trying to work out, well, what does symmetry mean if there's no non-trivial groups? And mathematicians came up with this idea of a pseudo-group, which is apparently hard to pin down a definition for. But eventually these came to be known as inverse semigroups. Pseudo-groups are kind of like inverse semigroups where you think everything is a homeomorphism or something like that. And another approach to this problem used not semigroups, but ordered groupoids. So groupoids meaning, you've got these bijections, you're only allowed to compose things when domains match up perfectly, but there's an idea of being able to restrict these things as well. So these both involve, like I said, partial or local symmetries, and eventually, and I mean really eventually, there's this nice theorem that says not only is this kind of two different ways to look at the same thing, but it's essentially the same way to look at the same thing, just with different languages. And this result that's now known as the ESN Theorem, named after these three mathematicians, states that the category of inverse semigroups, looking at things this way, is isomorphic to the category of a certain class of ordered groupoids that are called inductive groupoids. So I'll tell you about the meaning of all these words and explain how this theorem works shortly. But this is kind of a culmination of many people's ideas. So Ericsson was one of the people that was looking at things with the groupoid approach. Boris Schein, one of the two main BSs in semigroup theory, was responsible for noticing this connection between an abstract inverse semigroup and a ordered groupoid, and he kind of showed how to construct one from the other. And it was Nambooripad who put this whole thing into a categorical framework where we're not just thinking of building categories from semigroups and vice versa, but morphisms are preserved, and in fact the entire category of structures is essentially one and the same thing. All right, so let's talk about what inverse semigroups are, and in fact let's even talk about what semigroups are. Sometimes when I'm speaking to people that do higher category theory and representations, whatever, I just tell them think about your own special thing and just forget everything except a single binary operation, and you've probably got a semigroup. So anyway, a semigroup in the simplest form is just a set with an associative binary operation. So a group is a semigroup, for example, or if you have a ring, just forget the addition, you've got a semigroup. All right, and what's an inverse semigroup? It's a semigroup that has something like inverses. All right, so when we think about inverses in groups, we think about things that completely undo elements. In semigroup language, an inverse of an element A is an element A dash satisfying these equations here. Okay, so A dash doesn't actually undo A. It's almost like it takes it back where you started. So imagine you throw an egg onto the floor. We don't have an operation that puts the egg back perfectly, but if you can pick it up, put it back where you found it, and then if you threw it on the floor again, essentially you've just done it once. Okay, kind of like it lets you start again. Okay. All right, so this element A dash is called an inverse, but in an inverse semigroup, we assume that every element has a unique inverse. All right, in some semigroups, elements can have multiple inverses, or sometimes you have no inverses. In some semigroups, every element is an inverse of every other element. All right. But in this case, because we've got a uniqueness assumption, it's kind of like we have a map to itself that sends every element to its unique inverse. And the usual symbol is A inverse for that element. Okay, now, of course, we can form A inverse and A inverse A, but the semigroup might not even have an identity element, and even if it does, these don't have to be the identity element, and they don't even have to be equal necessarily. So again, think of something like an exponential function and a log function. You compose them in two different directions. You're not going to get the same map. All right, so it's important for later to think of this as a second operation on S. So think of S as an algebra that has a binary operation and a unary operation. All right, what is a group? It's an interesting exercise to show that a group is just an inverse semigroup where you drop this second part here. So no one tells their group theory students that that's what a group is, but it's a fun little exercise to show that that's equivalent to the usual definition. And this is not a one-line proof or anything. It's actually moderately challenging. So if you haven't seen something new about groups for a while, give that a go. And later on, we'll see groupoids And I think of these as kind of like an algebraic thing rather than huge category. It's just a set that you can compose some elements, and every element is invertible. Okay. So what's the idea of inverse semigroups modeling partial symmetries? Well, I'll take it to the most basic level. So we'll take a set. We all know that a permutation of the set is just a bijection, and the set of all of these things forms a group, the symmetric group. And what's a partial permutation? Maybe partial bijection is a better term, but it's basically you just take subsets of your universe set, and it's a bijection between such subsets. Okay, and the set of all of these things is called the symmetric inverse monoid, and it's an inverse semigroup. The identity map on X. So these don't have to be proper subsets. It can be X itself. So every permutation is also a partial permutation. But the set of all these things forms an inverse monoid, where the operation, the binary operation, is just composition, where we compose things whenever we can. So just think like when you ask your calculus students to compose root X and other things, you just compose it, and the domain gets shrunk if necessary. And the semigroup inverse operation is just inverting maps. Okay. So let's look at some examples of this. Here's a perfectly good partial bijection. Here X is just set 1 to 6, and this map 1 to 3, etc. Its inverse is just it. And if we compose these two, just like usual, you follow the lines through, and you'll get this map. So that's alpha inverse. Generally, I mean, we're composing from left to right, and you get this. If we compose it in the other direction, alpha inverse first, we get this thing. So you can see this is an example where these two compositions are not equal. So they're not equal, and they're not the identity map, but they are identity maps on subsets. So this will, you can see why this will always be the case. Alpha inverse is just the identity map on the domain of alpha, and the other one will be the.
In this case, they're idempotents. Right?
Yeah. So in fact, always alpha inverse will be an idempotent. Yes. Yeah. That's really important. But in particular, if we compose this with another alpha, we're just sticking an alpha here, and what we're doing at the start is just mapping its domain identically. We're just going to get alpha. So you can see how these laws hold, and why the inverse map is actually a semigroup theoretic inverse. All right, let's compose these. So here are two sort of randomly selected partial permutations. How do we compose them? Well, we've already been composing things. We just connect them up and follow the lines through. So that's alpha beta, and that's very easy because I didn't really randomly pick these. I picked random things, but made sure that the domains and codomains matched up. Okay. I'm not claiming that it's actually difficult to compose these things when the domain and range don't match up, but it's easier when they do. So when you compose these guys, all that happens is you see which lines actually make it all the way through, and you throw away the other ones. So composing these things will end up with this guy. Okay. And although, like I said, this is not super hard, the very basic philosophy behind this ESN theorem is that somehow you want to only know how to do the easy things and sort of see this and try and turn it into an easy thing. So it's not hard to make this easy. So let's see what we should do. Well, what we're going to do is we're going to take, we've already pre-calculated this thing here. We're going to let alpha dash be just those lines. Beta dash, sorry, gamma dash be only those lines. So we'll just sort of throw away the hard bits, and then we've got an easy composition. So somehow we turned this composition on the left that I'm still calling hard, and replaced it with something that's easier, we're just basically restricting the two maps. So what we're doing is you can kind of think of, well, this one, gamma dash, is just the restriction of gamma, this here. Whereas alpha dash is the restriction to the same set, but we're kind of restricting the codomain rather than the domain. So we've kind of got two different kinds of restrictions, the left and the right. And of course, 3, 4 in this case is just the intersection of the image of alpha and the domain of gamma. All right. So this is where we've been working, the symmetric inverse monoid, and we're kind of turning it into this thing that you could call the symmetric inverse groupoid, where we take the same underlying set, partial permutations of our X, and we only remember the easy, what have been called the easy compositions, the compositions where domains and codomains match up perfectly. So the objects in this case we think of as all of the subsets, and remember elements of this thing are bijections between subsets. So if we're given a pair of subsets A and B, we think of the morphism as just bijection. And we only compose these things when the codomain of alpha equals the domain of beta. All right, and I've told you that if you've got an arbitrary pair of bijections, you can always turn their semigroup theoretic product into a groupoid composition just by suitably restricting these guys. All right, so how do we formalize this and make it completely abstract? So we'll take an arbitrary inverse semigroup, which remember means every element has a unique inverse. It was mentioned before, I think Stephen said that A dash is an idempotent. If you just look at this equation here and multiply it by A dash on the right, you can see straight away that A dash is an idempotent. And essentially what we're going to do is think of this as the domain of A, and this is the codomain of A, or the range of A. So we're going to make a category where these are the domain and range of A. So as usual, we let E be the set of all idempotents of S, all the elements squaring to themselves. And it's a fact in inverse semigroups that products of two idempotents are always an idempotent. In fact, two idempotents always commute. So we get a commutative subsemigroup. For an arbitrary semigroup, idempotents don't necessarily form a subsemigroup. So this is called the semi-lattice of idempotents because there's an order theoretic property of this. And it's basically that you can turn this commutative semigroup of idempotents into a poset where you say one element is below another if it's kind of like a zero element of the other one, or if you like prefer to think of it, this is an identity element of the first. And because these commute, this means E is the left and right zero of F, or F is the left and right identity. And with respect to this partial order, every pair of idempotents has a greatest lower bound called the mean, and that's just their product. Right? And conversely, if you have a semi-lattice or a poset where every pair of elements have a mean, you can just define, well, mean is just a semigroup operation on that set. Okay, so E is a partially ordered set, and that turns into a partial order on the entire semigroup. As follows: you just say A is below B if A is B times an idempotent in on either side implies the other. All right. So how do we use this to form a category? We're going to do so like this. We think of this as just the morphism set is exactly the same as the underlying set of the semigroup. The objects are the idempotents. And we think of the domain of an element as being this A inverse, and the range as being A inverse A. Sure, I had bold D's and R's before anyway. And all right, because A inverse A equals A, that's just telling us that the domain of A times A equals A. So this is a left identity for A. Something similar happens with the right identity. And there's this very important property that if the range of A equals the domain of B, so if A and B kind of match up, then when you find their product, the domain will be the domain of the first, the range will be the range of the second. So this is the important property that lets us define a category. So we so if A and B are such that A inverse A, B inverse, then AB is going to map from the domain of A to the range of B. Okay, so the range of A is always the domain of A inverse, just by looking at these equations here. So we can compose things, and if we can compose them, then we just, well, the composition is just defined to be the products, and that's just defined to be the domain of A. So with a similar calculation for the range, this tells us that we've got a groupoid. Every element is invertible, and the inverse in the groupoid sense is just the semigroup theoretic inverse. Okay. So given an inverse semigroup, we've got this groupoid, and we want to understand how to go back from the groupoid to the semigroup. So how do we do that? The first way well, the first thing we have to consider is that now if we forget the semigroup we started with, and we've just got this groupoid, we've just got a bunch of objects and morphisms, and we might have something like A and B, which we can't compose because they maybe don't have the right domains and ranges, but we want to multiply these in whatever semigroup this thing comes from. So we have to somehow work out how to do that. So the key point is that we've got this order on our semigroup, and we can turn this into a property of what we call restrictions. So if you have a morphism and you have an idempotent that is below the domain of this thing, it's possible to define, well, in the semigroup, remember we are actually in a semigroup, we define the restriction of A to this smaller idempotent to just be the product of A by E on the left. Okay? And this kind of restriction and its right-handed version satisfies the axioms of an ordered category. Okay? And it turns out that A is below B in the order we defined before, precisely when A is an idempotent times B. I didn't say that idempotent has to be below the domain of A, but there's always some idempotent. If A is some idempotent times B, you can always replace that idempotent by something smaller. So A is below B precisely when it's a restriction. Okay, and now imagine we've got any two elements of our groupoid which we want to compose. We're going to let this be E, this be M. Then A is AE because E is the range of A. Similarly, B is FB. So we're going to let G be the product of these guys, which remember is the mean. That's right. So that's below both of them. And if we just calculate the product in the semigroup, so remember we are actually in the semigroup, apply those laws there. EF is in the middle, so that's a G. G is an idempotent. And because G is below A, this is actually a restriction of A to G, and similarly B to G. And since this has domain range G and domain G, this is an example of a product where domains and ranges match up. So somewhere below A is A restricted G. somewhere below B is B, which is G, and we can compose these guys in the groupoid, and this just shows that their composition is exactly the product in the semigroup. So so if you start from a semigroup and form this groupoid, you can go back. Okay. Now we just want to know what are the exact groupoids that we get from this kind of construction. So that's the idea of inductive groupoids. So Lawson defines an inductive groupoid to be an ordered groupoid. So a groupoid with an order that just respects everything, and whose object set just happens to be a meet semilattice. So we've got this groupoid. Start with any groupoid. It's got an object set that inherits a partial order from the groupoid, and if that partial order on the objects just happens to be a semilattice order, then that's what we call an inductive groupoid. Okay, and given such a inductive groupoid, we can define a semigroup. So now we're imagining we're not even starting with a semigroup in mind. We've just got this groupoid satisfying these axioms. We define a semigroup who has the same underlying set as our groupoid. The inversion doesn't change, but the product is given just as before. So given an arbitrary A and B, which may or may not have a composition in the groupoid, we find the range of A, the domain of B, we go down to the meet, and we restrict each of A and B to this common lower bound, and then we compose the morphisms like this. And you've got to prove that this is an associative product. That's the tricky part. Yep.
Yes. So when you say the underlying set is the groupoid, it's
Yeah, the morphisms of the groupoid. So I'm thinking of groupoids as just an algebraic thing. So we've got the main thing of interest are the morphisms. Yeah. All right. So somehow, I don't know, but all the bold symbols have not worked. So anyway, starting from a semigroup S, an inverse semigroup S, we can construct this inductive groupoid, G of S. And starting from an inductive groupoid, we can construct a semigroup S of G. And the main idea is to show that if you start from a semigroup, construct a groupoid, and then go back, you get the same semigroup, and vice versa with groupoids. And this ESN theorem says not only do the processes undo each other, but they're actually category isomorphism. So it maps functors to functors, well, semigroup homomorphisms to functors of this groupoid, and they're inductive functors, meaning that they preserve meets on objects as well. And well, sometimes when a semigroup theorists look at a result like this, they think semigroups are so easy. Why would you care if you can think of them as something crazy like a groupoid or something like that? But I know that in this room, no one's going to say, why would you want to categorify something? But one answer to the semigroup theorist is that if you want to check that a map is a semigroup homomorphism, you know, you've got to check that phi of AB equals phi of A, phi of B. If you want to check that something is a functor, you only have to check that in the easy cases where the domains are wrapped up. So that's one motivation for actually wanting a result like this. And when you go to something more complicated than inverse semigroups, where products can be really messy, like diagram algebras, where you stick two things together and it's not just a case of what falls off, but what complicated gluing happens in the middle. This is actually a really significant advantage. All right, so let's move on. So I've sort of told you the story for inverse semigroups. That's what they are. The most obvious sort of generalization of an inverse semigroup is called a regular semigroup, where what we assume is that every element has some inverse, not necessarily a unique one. Okay, and these are these two classes of semigroups are probably the most studied classes of semigroups. apart from groups, obviously, but no one really thinks you're doing semigroup theory when you're doing group theory. But there's a sense in which regular semigroups are way too far of a generalization. So every element has an inverse, doesn't have to be unique. There's an extremely amazing paper by the Indian mathematician Nambooripad, who is a little bit of like a Ramanujan of semigroup theory. He just sort of popped up in India and wrote this amazing thesis where he extended this inverse stuff all the way to regular semigroups. And there's a quote by John Meakin, one of the sort of senior semigroup theorists, that said he only tried this because he didn't realize it was impossible. And I think that's a good analogy. Like sometimes you work really hard, and what you finally get, you think, if I knew at the start of this project it was going to be this hard, maybe I would have done something else. But you know, I'm glad I did try. So there's a kind of idea where you've got A. If it's an inverse A dash, you might want to think of this as a map from A dash to A dash A. But the problem is that A might have another inverse, A double dash. So maybe we should think of this as a morphism between those idempotents, and they might be completely different idempotents. So something kind of difficult happens, and there's a lot of care that goes into Nambooripad's construction here, and it's really not a simple thing to talk about. You also don't get a result that says this category is isomorphic to this category, but there's some kind of equivalence of categories. So today, I'm going to talk about our paper, which concentrates on a class between these two, called regular star semigroups. They fit into the general scheme of things like this, where if you imagine, you've got the whole world of semigroups, which is just absolutely wild, and then you kind of bit by bit go to the very symmetrical case of groups. Inverse semigroups are kind of the next case out. Regular semigroups are kind of the first attempt at trying to make things symmetrical, but they're still too crazy. And we found that regular star semigroups, which we're interested in for all kinds of other reasons, seem to be the absolute sweet spot between something that's a bit more interesting than inverse semigroups, but has enough structure and enough symmetry to let this groupoid stuff happen without the crazy complications that happen with regular semigroups. I kind of think that, if you've got a regular semigroup or you've got this insane Nambooripad category thing, maybe that is a bit of a stretch. But I think it's fair to say that the categories we found for regular star semigroups are pretty nice. All right, so one way to motivate the class of regular star semigroups is to look at inverse semigroups in a different way. So I mentioned that semigroups are just the algebras with a single operation that satisfies the associative form. Okay, it's just a single identity. So that means semigroups form a variety, not a algebraic variety, but like a variety in the universal algebra sense. It turns out that inverse semigroups, if you think of them as an algebra that has a binary operation and a unary operation, well, it should satisfy A dash A equals A, because that's just one of the meanings of being an inverse. It also happens that the inverse of an inverse is itself. That's might seem like an obvious point, but it's not easy to prove that in inverse semigroups. Also, the inverse of a product is the product of the inverses flipped, just like for groups. But again, these are not completely obvious consequences of the definition. This last equation is a little bit easier to see why it holds, because AA dash and BB dash are both idempotents. I mentioned idempotents commute in inverse semigroups, so this identity holds. That also is not easy. So a lot of these very basic properties of inverse semigroups are they're elementary, but if you try and discover the proof, it's not easy. What's really interesting is that any algebra with a binary and unary operation satisfying these laws happens to be inverse. So this is actually a complete set of identities for inverse semigroups. Okay, what's a regular star semigroup? Well, you just cross out this last identity. Right? So that's the easiest way to say what a regular star semigroup is. The semigroup of an associative binary operation, and it's got a unary operation, which now we're going to call star because it's star semigroups. Satisfying things. So if we call this first one, basically star is an involution. Okay? And a star is an inverse of A. So it's kind of like a semigroup with a special kind of involution.
You're actually picking an inverse.
Yes, I'm really glad that you said that. So yeah, it's kind of like if you go back to this picture, in groups, everything is invertible. Okay? In inverse semigroups, everything is invertible in a different sense. Every element has a unique inverse. In regular semigroups, every element has some inverse, but there might be 5,000 of them, and there's no way to say which one is the right inverse. Whereas inverse semigroups kind of pick the inverse for you, and there's just one choice. In the regular star semigroup, there's a very distinguished one. Yeah. All right, so regular star semigroup, like I said, is a semigroup with a special involution. And we think of it as a basic operation. So S is an algebra with two operations. So if you just give me a semigroup, it might be possible that there's a star operation and a hat operation or a dagger operation that also satisfies these laws. And it's quite possible to have many different ones. But inverse semigroups have a unique one. It has to be the inverse. All right, so examples include, of course, inverse semigroups, and it turns out that they form a somewhat simplistic example of what we're doing. Just like, you're not going to apply semigroup theory to groups and see what special results you're going to get. But the main motivating examples for myself are diagram lines, which I've been studying for the last many years, and probably are familiar to lots of people in this audience. Partition monoids, Brauer monoids, you would probably think of partition algebras, Temperley-Lieb algebras, but these are the monoids underlying those algebras. So let's just quickly remember that a partition monoid, here I'm just going to talk about P6. We've got 6 vertices and 6 dashed copies of those vertices. And by a partition, I mean a set partition of those vertices. Okay, this is a graph that represents such a partition. You don't take the edges too seriously in the sense that this edge could have been here. All that's important is that it connects the right vertices together to form the blocks of the partition. Okay, so this forms a monoid, and in fact it forms a regular star monoid, where the star is the usual involution on these monoids and algebras, where you flip everything up. It's kind of not too hard to see that if you flip something and then flip it again, and you've got the thing that we started with. It's not massively hard to see that if you do AB and then flip it, you may as well have just flipped them both and then done the other way around. So it's actually not hard to see that this is a regular star semigroup, but in fact showing that the binary operation is associative is a bit tricky. All right, so what is the binary operation? We connect our partitions together. I'm just going to let loops float away. So we end up with this. Then we just see what's connected. And people who've worked with these things will immediately see that I've massively cheated in the example that I picked, because the bottom of alpha matches top of beta just so perfectly that it looks like this is the easiest thing that you could ever do. Okay. But more realistically, when you randomly pick some partitions, things are going to have all kinds of mess in the middle. Things are going to join up. It's not even just a matter of two things might join up. There might be all these complicated paths wiggling through the middle. And things get even worse if your base set is infinite. So you can have partition monoids on a set of any cardinality you like. All right, so I'm not going to go through the exact way we calculate this. We just basically stick the pictures together, only look at the top and bottom, and then just see what gets stuck. All right, and our basic sort of philosophy from before is we want to turn something like this, which is in some sense hard, into something easy, like on the previous page, where things just match perfectly. Anyone can do products where they match perfectly. It takes me a long time to do products like this. I just want to simplify everything. It turns out that it's not always possible to do this, but it is possible to find nice alpha and beta below alpha dash and beta dash below alpha and beta, and something also nice to stick in between. So something that kind of we can reduce our complicated things at the expense of putting something in the middle, like a sandwich filling. All right, so in this example, alpha dash and beta dash, I really don't want to go through too much, but we basically, it's almost like with our alpha dash and beta dash before, we kind of throw away a few bits of our original things. In this case, we might throw things away and we might stick some things together. These things still don't match, but you can actually look at the bottom of alpha dash, look at the top of beta dash, and make an epsilon that matches them perfectly, and maps through wherever it should. Okay, and this is just a cooked up example, but it comes from the general theory that I'm going to try and talk about. All right, so let's try and play the game we did before with inverse semigroups, but now do this with regular star semigroups. The idempotents played a really important role with inverse semigroups. They gave us the objects of our groupoids, but it turns out that there's an even more special set, which we call projections. They're just the idempotents that are also fixed by the involution. Okay. The idempotents of an inverse semigroup always formed a subsemigroup, but that's not the case here, neither do the projections. So to spell that out, if we have two projections, then their product might not be a projection. It's actually always an idempotent. That's an interesting property, and projections always play an important role in previous studies of regular star semigroups, but even more so here. But even though PQ is not necessarily a projection, PQP always is. So you can kind of conjugate projections by each other, even though you can't just multiply them. So if you think about it, P is conjugating Q. And if we took any Q, P would conjugate that to some projection. So P is, you can think of it as a kind of map from the set of all projections to itself. So every projection determines a map, I call it beta P. And it just maps a projection Q, so this kind of conjugate. Because P is a projection, you can kind of think of this first P as P star, and then it's really like a conjugate, P inverse UP. And every element of P gives us a map like this, and now we want to think of that map as unary operation on P. So we've got a set, P might have 10 elements. It's now got 10 unary operations, one for every element of the set. So these are the operations. So instead of a semilattice, we're having a funny algebra with lots of unary operations, and we call this thing the projection algebra of I should say the projection algebra of S actually. What is theta P applied to P? Well, it's just PPP, which is just P, because every projection is an idempotent. So there's an identity that's satisfied. Another identity is that if you do theta P operation and then do the same one again, well, you've just got a PP here, which is P. So these operations are themselves idempotent. And there's a bunch of other laws that you can quickly figure out. And it turns out that these give a complete axiomatization of the unary algebras that you will get from regular star semigroups. So if you have any set with a bunch of unary operations satisfying these laws, there'll be some regular star semigroup that has exactly those projections, behaving just like these do. All right. So this is exactly the same page as before with inverse semigroups, because it turns out that the laws you need to define the groupoid coming from an inverse semigroup don't include needing idempotents to commute. We take the morphisms of that category to just be the elements of the semigroup. The objects are now not the not all idempotents, but just the projections. And the domain of an element is A star. The range of an element is A star A, and it's not too hard to show that this is the projection. So we've seen that it's an idempotent, and if you star this, you get A star star, A star, and that's the A star. Okay, all of the same things happen. The domain and range are left and right identities. This law holds, and that lets us define a composition. So A circle B is only defined in this sort of nice matching case. This is just what I've had before. So we've got a groupoid, we've got the same involution, but we don't have an inductive groupoid necessarily, because the object set, sorry, I'm saying the G for the object set, it's a projection algebra rather than a semi-lattice. So we've got a different kind of groupoid here. All right, so we've got the basic philosophy is we've started with a regular star semigroup. We've made a groupoid. Okay, the object set is a projection algebra. The composition are just the easy products. Inversion is just the involution. And it turns out that it's possible to recover all products, not just as a restriction of A with a restriction of B, but we've got something else in between. What are these? Well, P dash and Q dash, as before, are something below A and B. They're kind of like the closest you could find to a meet of the two things, but they just might not be quite the same. But then there'll always be something nice mapping between these two things, something completely canonical. Basically, this is just having the inverse case going to be A times P dash in the semigroup. This is going to be B times Q dash on the left. And then it turns out that P dash Q dash is an idempotent with the right domains and ranges. All right, so we have this this theorem that tells us that inverse semigroups correspond exactly to the groupoids that you get out of this construction, which turned out to be the inductive ones. And we, of course, hope that regular star semigroups are going to be some kind of groupoids, whatever these groupoids turn out to be. All right, so well, we start with what's an abstraction of these algebras of projections of regular star semigroups, and we just define a projection algebra to be a set with unary operations, one for each element, satisfying those axioms that I flashed up before. And whatever our groupoids are going to be, they're going to have object set some projection algebra, and somehow the structure of this projection algebra is going to have to interact with the structure of the groupoid. So we're going to have to be able to form restrictions. So a projection algebra, it's not obvious from this, but there's a partial order that I'll put up in a minute. And whenever something is below the domain of A, we should be able to somehow restrict, likewise with the codomain. And there should be some way to find something here that plays the role of the idempotent epsilon from the case that we know we started with a regular star semigroup. And whatever this element is, it's going to have some nice property so that this thing ends up being associated. So it's enough to show that the inverse semigroup product was associated, but now we've got this extra term. So when you do A times B times C, you end up with 5 morphisms that somehow have to commute. Now, you can just write down this is associative as your axiom, but obviously you don't want to do that. But you could also write down all kinds of things that prove it's associative, but you just don't want to put down too many things that don't actually hold in regular star semigroups. So this was a big this was a big hurdle for us. All right, so I mentioned the partial order. You just say P is below Q if P is fixed by the operation Q. And in the case of the partition monoid on 2 elements, this is the Hasse diagram of the order. There's a bunch of other relations which we use the symbol F for friendly. And if you think about this in a semigroup, this P is PQP. So it's kind of like P and Q are somehow inverse of each other. So that's this F relation. P is PQP and Q is QPQ. So P and Q are inverse of each other. So it's a very nice situation where two projections are inverse of each other. We say that they're friends. Okay. And once we've got this is part of the picture for PE5, partition monoid of degree 5. You get very nice symmetrical graphs of these things. All right, so given a projection algebra, we want to define a class of groupoids that have these as object sets. And the first ingredient is what we call the path category. This is essentially a free category on this relation, like that. So we've got this F relation from the previous slide. And now we just consider sequences of projections where this is rendering this is rendering this, and so on. They're not necessarily all friendly, it's just a chain of friends. We all know that, you know, if I'm your friend and you're their friend, I'm not necessarily their friend. And we think of this as a morphism from this guy to this guy. So we scatter around our projections, and between them we have morphisms, which are just sequences that link us. So friends of friends of friends of friends of friends. And how do we compose these things? Well, if they agree in the middle, we just stick them together and identify that middle guy. So this is a nice category, and as I said, it's just a free category where you just have an edge between every friend, every pair of friends. But we want a groupoid, so we actually quotient this category by identifying a bunch of things. So if I saw a P and then a P in a path, well, if I'm thinking of these things as projections, I want to just identify those to just be P. All right, so we want PP to be equivalent to P. If P and Q appear next to each other in a path, then they're friends, and so therefore PQP equals P, at least in our heads. So we should think of the path PQP as being equivalent to P. There is one other axiom that I'm going to gloss over a bit, but it's necessary for later. We identify certain paths of the form EF with something in the middle, two different somethings, depending on what they are. And when we quotient out by these things, we get a groupoid. Because if you think about a path, you know, PQR, if you compose that with RQP, you're going to get a whole bunch of these guys in the middle that are just going to cancel out, and everything ends up as just the domain. All right, so the inverse of a path, or an equivalence class of a path, is the reversal of the path.
So let's move that time back up.
Sorry. Okay. Let's yeah. So basically, I'll try and give you the 2-minute version of the theorem, which is that you start with an ordered groupoid that has a projection algebra for its object set. We have some axiom that links the structure of the projection algebra with the ordering in the groupoid. It's too technical to really say explicitly, but it's a little bit like one of those projection algebra axioms. The epsilons that allow us to form the total product on our groupoids come from these chain groupoids. So let's skip to this. So we start with a groupoid. It has a projection algebra. It has a projection algebra, let's say P, for its object set. From that projection algebra, we construct a chain groupoid, and we just have to have a way to somehow interpret that chain groupoid within that groupoid. So somewhere there's a an image of this chain groupoid. And there's this condition that links everything together, which basically says whenever we've got a morphism and a suitable collection of idempotent projections below the domain and range, we can restrict these things, and then we can go around this diagram in 2 different ways using our epsilon evaluation mapping, and we should get the same thing. And this is exactly what we needed for associativity. So that's the idea. 2 morphisms, you restrict them to something, you put an image of this chain groupoid in the middle, that gives you your product. We spent a long time to prove this is associative. You would think semigroup theorists would just do that very quickly, but we didn't. And then you can go backwards and you end up with this here, which is that the category of regular star semigroups is isomorphic to the category of these groupoids that we axiomatized. So that's nice. It lets you think of semigroups as groupoids, and the second part of the paper has a bunch of applications. I won't be able to explain exactly what these are, but they give kind of like a regular star version of some classical theories that are nice in some regular cases, but somehow fail spectacularly for things like partition monoids. These give examples, analogs where everything seems to work. So it's very nice. So we've got certain free objects, and we can construct these things called regular fundamental semigroups, which had been constructed before, but no one knew why there was this weird thing in the middle. And it turns out that if you construct groupoids rather than semigroups, things are easier, and our construction just says you just have to have this thing in the middle. So thanks again.